Okay, now we're going to talk about not spherical lenses, but thin lenses. And I think I put an E on the end. I'm not supposed to. So this is an example of thin lens. So it has surfaces, and the key thing is that there are a couple of key things, as you can see from this drawing. A ray that comes parallel to the axis is refracted and goes through the focal point of the lens. There's a focal point on both sides, because this case it's asymmetric lens. So light goes through the focal point, goes through the mirror, parallel lines go through the focal point. And then it passes through the focal point, continues on down here. If you come from the object through the center of the lens, it just goes straight through. So you refracted a little bit, but then you refracted the same amount in the second half. So there might be a slight offset, but it's not very much. And so you just draw a line straight through the middle of the lens. So it's the middle is the intersection of the horizontal axis and the center of the lens. Goes straight through there. So you get 2 points. There's also a third point. The third way of doing it is if you go through the focal point and come to the center of the lens, and then those lines should go parallel to the axis, and so you have a third point if these are all drawn correctly to scale. So 2 out of 3, either one of those you can do. Okay, so you have to be given, or you have to be given the focal length, or if you're given the distance of the object from the lens, which is the distance from the center of the lens to the object, and if you're given the distance from the lens to the image, then you can find the focal length. And there's the lens equation, so I'll write that out. It looks very similar to the mirror equation, and really is the same thing. 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. It turned out for mirrors that the focal length was equal to r over 2, so when you put r over 2 in there, you get 2 over r when you take the reciprocal of it. So this is the lens equation. There's also an equation for the magnification. So m prime, actually it's not m prime, it's just m. And in this case I'm going to use the terminology that's shown. So this actually, using their definitions, you'd say 1 over s plus 1 over s prime is equal to 1 over f. And I guess it'd be f2 on this side. Okay, the magnification, which I'll use their terminology, which is h prime, the height of the image over the height of the object, is just equal to negative q over p. So what you can do there is you can see the negative sign, which means that the object is inverted. You can see that. I mean, the image is inverted. So the object is pointing up, the image is pointing down. That's what the negative sign means. And relative to the focal point, if you're outside the focal point, then the image is smaller than the object. If you put it inside the focal point, the image is larger. So when it's here, you can think of a camera, which takes an object, takes the light from an object, puts it through a lens, and then puts it on a piece of film, which is much smaller than the actual object is. The case where this thing moves inside is a projector. So you can either magnify or you can make it smaller. Also, this is called the lensmaker's equation. And in your book it says 1 over f is equal to n minus 1, where n is the index of refraction of the lens, times 1 over r1 minus 1 over r2. 2. So these are the radiuses of the lens. Okay. So what we'll do is we will look at a couple of examples in terms of the different cases, the case of the camera and the case of a projector. Notice there are some angles defined. So alpha coming in is equal to alpha coming out. And likewise, when you've got this angle beta here and an angle beta there, you've got a line being cut to the intersection of two lines, the opposite angles. They're called vertical angles, and they're equal to each other. Okay. So I think that's all we have to say.